Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today we are going to talk about amino acid, peptides and proteins. To discuss this topic, we have with us our subject expert Dr. Pankaj Khanna. Dr. Khanna is Assistant Professor in Department of Chemistry in Acharya Narendra Dev College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture.
Thank you.
Welcome, sir.
Thank you. Hello viewers, today we would be starting where we left the last time. We talked about in the previous lectures that amino acids are the basic building blocks of proteins, and they are also, proteins may be further divided into peptides, and the smallest unit is available is the amino acid. So we talked about the acid base behavior of amino acids and all. Then we would be starting with the synthesis of alpha amino acids. So these are the amino acids which are a part of proteins and peptides, and we would be knowing how to synthesize them in the chemistry laboratory. So I have given here certain number of ways of synthesizing these alpha amino acids. We would be doing it in this session or in another session maybe. So and there may be some of the combinations of the synthesis that are not mentioned here. So we would be tackling those also in between. So starting with the synthesis of amino acid, we should recall that the alpha amino acid which is present in the peptides and proteins has a general structure of this kind, the NH2CHR CO2H or COOH, and this structure we require an amino group or an amine group and a carboxylic acid group. So we want to, when we want to synthesize this molecule, we need to have the NH2 group and the carboxylic COH group in place with a certain long chain of the carbon, or we may call as a hydrocarbon chain, or with some other substitutions. So we are not going into specific synthesis of amino acids, like we are synthesizing the 20 amino acids specifically, but we are giving here the general synthetic methodologies which may be given for the synthesis of those many number of amino acids. So to start with, in the structure, I have put a dotted line here. That means I can go about the synthesis of the amino acid in two ways. Like I can divide this molecule into, I can remove the NH2 group, and we may say that you can see here that this RCH COOH group forms a carboxylic acid group. So what I am trying to suggest here is that this NH2 group may be introduced. The second, introduced into a long chain of carboxylic acid. So the maximum number of methodologies we are doing today are all on this methodology of introducing an amine group into a chain of carbon atoms, and the chain is selected as such that the carboxylic acid appears here because of the reactants. So for this purpose, we sometimes we are using the carboxylic acid long chains, or we are using the active methylene groups, or we would be doing it one by one. So this is one methodology of introducing the NH2 group. The second may be the introduction of the carboxylic group to a chain of amine, but this is quite a difficult thing because to introduce a carboxylic acid in the presence of amine is sometimes it may be a cumbersome process. So we do not follow much of this process that we introduce carbon dioxide later on. But the third thing I have not mentioned here is that the important point is that we have to, sometimes what we do, we take a carboxylic acid chain and we introduce the R group, and then we introduce by a certain method the NH2. So there may be a third way of introducing the R. So what I am doing right now is called as the retro analysis or the backward analysis of the synthesis of these amino acid. So, by doing retro analysis, the basic model which comes out to be is we would find out sooner than later that this NH2 group is coming to a system of a synthon which is having already a carboxylic acid producing group, and simultaneously we are adding, sometimes we are adding the R group, or sometimes we are taking this long chain thing and we are introducing the NH2 group. So, let us start with this. The first synthesis is the reductive amination of alpha keto acids. So, alpha keto acids, what are alpha keto acid? Alpha keto acid is, this is carboxylic acid carbon, and the next carbon is having a C double bond O group, which is the, we may say that the carbonyl group which is present here. So, we are having R as a substituent of the, as generalized as an alpha keto acid. What we do with this? We react this molecule with the reactant, that is ammonia. When we react this alpha keto acid with ammonia, what we get is a kind of, whenever a carbonyl group is reacted, you would recall that a carbonyl group undergoes nucleophilic addition reaction with NH2G type of compounds. You must have done at the school level also, and they give the C double bond N-G type of compound. So, in this case, because the G group is hydrogen in this molecule, NH2G means H is the hydrogen ammonia. So, we are having C double bond NH, but with the C double bond NG wala compounds are stable when the atom attached as G or the groups attached are not hydrogen. So, this I have put in square bracket because this intermediate is not pretty much stable. It again goes back to the, it may go back to the carbonyl again, and it is present in a, in situ it is present, but it is not separated. So, I have put the square brackets here. When I do the reduction of this C double bond NH, I get the required amino acid structure we just saw in the previous slide. So, amino acid structure, we have got the R group which was present in alpha keto acid comes as the R group of the amino acid. You would recall that when we did all the classification of amino acids, then this R group was the, it may be a hydrogen for glycine, it may be a CH3 for alanine, CH2PH for phenylalanine. So, in that manner. So, if I take an example of this, I am taking this example as R is CH3 and I am using ammonia, and then in the second step I am reducing it with hydrogen and palladium. We may also do this reduction with sodium and ethanol, and I get what I started with was, this is pyruvic acid. You would recall from your earlier studies that pyruvic acid is a very important molecule in the biochemical pathways like glycolysis, Krebs cycle. It is very much important. So, we may say that somewhere down the line the molecule which is formed here as alanine is getting formed from pyruvic acid in some method in the organisms also, by in which ammonia is added, and there is some catalytic enzymatic catalysis which is happening on that this intermediate, and we get alanine synthesized. So, this synthesis, I have taken pyruvic acid, CH3 is coming here as the R group and we get alanine. So, in this manner we can prepare if I take glycolic acid like H and C double bond O COOH, then I would get glycine. If I take PH CH2 here, so it will be phenyl 2-oxo 3-phenyl propionic acid. So, I would get phenylalanine. So, in this manner I am giving you a general synthetic pathway for the synthesis of various amino acids. So, all these methods which I am giving here are not suitable for all amino acids, just because of the fact that there are other groups present, like in lysine there is an NH2 in R group, then there is the carboxylic acid group present in aspartic acid. So, all methods are not suitable for every case because the reactants are such that they may react with the side chain residue which we are interested in making to enter in the amino acid skeleton. So, moving on to the next synthesis, that is again I am telling you that we are introducing the nitrogen, the NH2 group into various substrates. So, next is again amination of alpha halo acids. Amination of alpha halo acids, what is done? Alpha halo acids, so I should give you the thing, you already know that firstly we should have the alpha halo acid. What are alpha halo acid? Alpha halo acid is like I have a general carboxylic acid, long chain carboxylic acid, and I use the HVZ reaction. What is HVZ reaction? Hell-Vollard-Zelinsky reaction, which is done under the PBr3 or Br2. We may have PCl3 and Cl2 also, and we get the chloro acid, the alpha chloro acid. Now we have here alpha bromo acid. So this alpha bromo acid is simply reacted with ammonia. Again I am introducing ammonia here. So again it is called as amination. So amination is should not confuse it with animation because they are tongue twister words. So amination is the introduction of amine group. So amine group is adding, how it is added to the alpha halo acid is the lone pair of this ammonia attacks on this carbon, and the attack is nucleophilic attack because of the presence of halogen. There is a positive charge on this carbon and the halogen leaves as bromide ion Br minus, and we have NH3 plus added here first, and then the hydrogen leaves as H plus. So we have HBr which is eliminated to give you the required alpha amino acid. So you can correlate that we were having alpha halo acids and now we are having alpha amino acids because the carboxylic acid is given the higher preference in the nomenclature. So taking another example of this kind, what I am doing acetic acid. I have done the HVZ reaction, and what is formed? It is alpha bromo acetic acid, and simply by the reaction with ammonia, passing ammonia gas on this, I would get the NH2 group here. So I would be getting, what is this molecule? This is glycine, because you remember that R is equal to H here. The H is coming as, this carbon is having CH2. So this R is H here. This was RCH2 and I am having CH3 here. So this is acetic acid I took and we got the glycine molecule. If I had taken, instead of acetic acid, I had taken propionic acid and did the Hell-Vollard-Zelinsky reaction, I would have got 2-bromo propionic acid and then finally the alpha amino acid which is alanine. So this is the way of doing alpha halo acids amination. But there is a point to be noted here that because we are doing the chlorine or bromine compound, the halo compound, we are reacting with NH2, the yields of this reaction are not very high. They are pretty much low because of the fact that the ammonia gas is being passed, and the ammonia gas should be in quite an excess. Otherwise, if the bromo acid is in excess, then what would happen? This alanine or glycine molecule or any other amino acid which is formed may again react with the bromo acid available. So I would have a secondary amine here rather than NH2CH2COH. I would have CH2COH one attached to this N and another CH2H attached to this N, and this hydrogen will go off. So I would have secondary amine, and if further ammonia is in pretty less amount, then I could have a tertiary amine also. So the reaction seems to be a little bit clumsy because passing of ammonia is again a little bit tedious job, and then the yields are pretty much poor because of these points I have told you. Another reaction which is well known due to its synthetic pathway and easy availability of the chemicals and the reagent is Strecker synthesis. Without going on to the yield part, but the reaction itself is very much understandably given very much importance in the synthesis of alpha amino acids, just because of the fact that the reactants are pretty much available and the reaction is pretty much fast. What is happening in this reaction? In this reaction we are starting with the aldehyde. So now the retrosynthetic pathway I talked about was about introduction of NH2 group, introduction of carboxylic group and having the R group introduced. So in this case we are not having NH2 group inside, we are not having carboxylic acid group inside, we are only having the alkyl or the R residue, that residue which makes the different amino acids, which gives the variation to the amino acid structure is present here. So I take the aldehyde and react with potassium cyanide. The reaction, you can see that when we are introducing potassium cyanide, it is a poison. So the reaction goes in a negative direction because of the fact that potassium cyanide is a poison, but if we do the reaction in a proper manner, there is no hazard, because if we are taking all the precautions, then there is no problem. So we are reacting with potassium cyanide and ammonium chloride. So what is happening? Potassium cyanide and ammonium chloride react to give you amino cyanide. The molecule which is formed has NH2 group in it and a cyanide group is there. And when I hydrolyze this cyanide group, we all know that in presence of acid and water, this cyanide group goes into the carboxylic acid form. So this methodology is using the nucleophilic substitution of nucleophilic addition of cyanide and then further the NH2 group introduction. So we would be taking a little bit of mechanismistic pathway of this reaction, because we should understand what this reaction is all about. So what are we doing? We are taking ammonium chloride. So even if we are taking it as ammonia, somewhere it is written as ammonia also, but this is the modification of Strecker synthesis which is widely in use, that ammonium chloride is used. What is happening? The carbonyl group is taking the hydrogen, the O is picking up hydrogen as H plus and getting protonated, and the remaining neutral molecule NH3 will attack the carbonyl group from the lone pair of nitrogen, and this nitrogen will attack this point. Why it would do so? Because you would remember that aldehyde ketones chapter, you would have learned that this carbon is pretty much having a large positive charge because of this electronegative oxygen atom, and there is a resonance in between. So this bond moves here to neutralize this positive charge and you would get the NH3 plus, and this OH, understandably this carbon is having a hydrogen here. So this would undergo a proton transfer to give you something like this, and the hydrogen H plus is moving from this place to the oxygen, and there is a removal of water to give you the C double bond NH structure, which was again present in the first synthesis we talked about. In the first synthesis there was C double bond NH, which was formed because of the ketonic group, the carbonyl group adding ammonia into it. So similar kind of thing happening here using ammonium chloride, but this is all happening in situ. It is not happening like we are doing the first step and then we are isolating something and then we are reacting it with the another molecule. So it is happening in one go, and the in situ preparation of this C double bond NH is attacked by the cyanide group, which is also present as potassium cyanide. So potassium cyanide is reacting here to give you the what is called as amino nitrile. This carbon is not visible, but C triple bond N, because it is planar and it is linear, not planar, linear molecules are all planar, it is linear. I have drawn it like this, and this carbon is the C triple bond N cyanide. So, this NH2 and cyanide we have got. So, what was the earlier reaction which was there? We have reached from aldehyde till this step by having cyanide and NH2 group in one molecule. Next, what we are doing with this amino nitrile, what we would be doing, amino nitrile we are taking here, and the amino nitrile we are hydrolyzing with the water in presence of acid. So, we are breaking the C triple bond N, and what is added? The OH minus is added here, and the H plus goes to the nitrogen. So, I have created this hydrolysis mechanism in a simpler manner for you to understand that sometimes we go typically by moving arrows and all, and we do not understand what is happening inside. So, what is happening, what I am trying to suggest here is that one carbon nitrogen bond is getting broken, and the carbon is forming, because carbon would be having a positive charge, it forms a bond with the hydroxyl ion, and the nitrogen forms a bond with hydrogen. So, we would be having COH, NH, and there is a double bond in between. Then another OH adding to this place, and the double bond is converted into single bond, and the nitrogen is having another H. So, we would be having COHOH and NH2. Last but not the least, the third bond is also gone, and we would be having that single carbon nitrogen single bond releasing NH3, 3 hydrogens and 1 nitrogen. NH3 is going off, and we would be having 3 OH groups on 1 carbon. If I am saying this, that 3 OH groups on 1 carbon, many of my chemistry friends, maybe teachers or students, would say I am saying certainly something wrong here, because even 2 hydroxyl groups cannot be sustained on 1 carbon. So, a carbon when has more than 1 hydroxyl groups, that is OH groups, undergoes dehydration to give you a carbonyl group, or we can say the C double bond O group. So, C double bond O group we get from what is called as the carbons having 2 OH. So, here we are having 3 OH. You can see on the slide that we are having here 3 hydroxyl groups, and when the 3 hydroxyl groups goes out of the 3 hydroxyl group, I have selected the 2, and these 2 get the dehydration done, water goes out of it, and what we get water. When it goes out, it gives you the required amino acid. So, what are we getting here? You can see on the slide finally that by the removal of water molecule, you get the required amino acid. You took the RCHO molecule in the Strecker synthesis, and you are getting the required amino acid. Thank you so much. Hello viewers, in today's session we would be discussing a few ways of the synthesis of alpha amino acid. Alpha amino acids may be synthesized in a number of methods, and we would be discussing the Gabriel Phthalimide synthesis first. So, you can look into the slide. The Gabriel Phthalimide synthesis of amino acid is the extension of Gabriel Phthalimide synthesis we use for the synthesis of amines. So, what we are doing here is we are introducing the amines into the skeleton such that we are having the amino acid form. So, what starting material we use? We use phthalimide and react it with KOH, potassium hydroxide, and get a salt of potassium salt of phthalimide, and this is reacted further as the alpha halo esters. So, we react this with alpha halo ester, and this nitrogen negative charge nitrogen is quite nucleophilic, more than the nucleophilicity is very high, and this carbon is having a partial positive charge because of the presence of bromine, and this nitrogen attacks here and removes the bromine as bromide ion. It goes off to give you this kind of the structure. So, what I am doing here is for the synthesis of amino acids, alpha amino acids, I am introducing the R group by this method, and I am also introducing the carboxylic group here in terms of the as an ester. So, what is next? Then I simply do the hydrolysis of this phthalimide using sodium hydroxide, and maybe you can say that potassium hydroxide and sodium hydroxide are one and the same thing, but we use these reagents as given by the synthesis. So, when you are giving an exam or writing somewhere, you have to use the same reagents because they come under the name of Gabriel Phthalimide synthesis. I may use any of the hydroxide, but because of the fact that they come into the name reaction, we have to use the same. So, what is happening? This carbon C double bond O N bond is hydrolyzed to give you a carboxylate and this long chain, and further on acidification you get the required amino acid and the phthalic acid as a side product. I have placed amino acid here as NH3 plus because I am adding HCl. So, HCl concentration, these amino group would be protonated. Even when we are synthesizing in a different manner, any manner we are synthesizing the amino acid, some books do write the Zwitter ion form of amino acid, but in this case the Zwitter ion would not be there because of the fact that we are having excess of HCl. So, HCl would protonate the Zwitter ion at the carboxylate ion terminal. So, we would be having COOH and this NH3 plus. Excuse me. I usually I am not writing in other reactions the Zwitter ion form, I am giving it as a simple NH2COOH form. Moving on to the next synthesis, I have written the complete reaction here. What I am doing here is I am introducing the carboxylic acid group in the amino acid by using diethyl malonate. It is an active methylene compound, CO2 ET, CH2 CO2 ET, and we all know that diethyl malonate is used for preparing n number of ways are there to prepare various carboxylic acid groups. How is it done? Carboxylic acids are prepared by the alkylation of this diethyl malonate. How we do that? We take the sodium ethoxide, create a carbanion here which is very much stable because of the extended resonance on the two sides, and that carbanion attacks the second reactant which is the alkyl halide, and the X minus or the halogen it goes out as a halide ion. So, R is attached to the carbon number 2 of the diethyl malonate. This we do in malonic ester when we synthesize, say if I have to synthesize butyric acid or long chain carboxylic acid, I would take diethyl malonate and do 1, 2 and butyric acid, I would add ethyl chloride and there would be a 4 chain system, and I would heat it and remove this carboxylic acid, I would get butyric acid. So, this was this is well known procedures of malonic ester, and I am using those procedures here to make the amino acid. The second step is KOH and HCl to hydrolyze these two esters, and we get this, the dicarboxylic acid molecule with a R substitution. Then we brominate it by using bromine, and there is another hydrogen which is present, which goes out and HBr is removed, and we get the bromine here. Out of this, when, as I told you that we can remove this one of the carboxylic acid by hydrolyzing and then heating and decarboxylation. We can heat it now, and heating and decarboxylation we get the alpha bromo acid. So, alpha bromo acid, simply saying this alpha bromo acid may also be prepared by using the Hell-Vollard-Zielinski reaction, but this is another method of doing this. So, this alpha bromo acid is reacted with NH3 and ammonia, and we get the required amino acid. But again, as in case of Hell-Vollard-Zielinski reaction or some other reaction, we get alpha bromo acid, this ammonia creates the problem in the yield of the reaction. So, what is done? There is a combination, we did phthalimide, Gabriel Phthalimide synthesis, and then we did the malonic ester synthesis. So, we can combine the two synthesis for getting better yields, or the chemist earlier may have, I am all reporting you the giving you the all reported procedures which are available in the literature. So, why they are doing this? They may have done because to get the poor yields given by the respective reaction, we convert them into a higher yield reaction, or there may be other reasons, we would be coming to that. And in this reaction, we are changing the strategy by brominating the active methylene group first, brominating the active methylene group, getting 2-bromo diethyl malonate, and then reacting this brominated compound with the phthalimide we did potassium phthalimide we did in the first reaction, first synthesis. So, N minus attacks here, bromine goes out, and we get the phthalimide attached to the malonic ester at the second carbon. So, there is one hydrogen there, there are two hydrogens here, one hydrogen here and one hydrogen here. Now, what we do, we have done, we have substituted the diethyl malonate with a nitrogen wala molecule, and now we can go for the usual malonic ester synthesis, and that is by taking a base. If I take sodium ethoxide, there may be a problem with the phthalimide ring or something like that. So, the literature reports that sodium is taken here and alkyl halide is taken here. So, sodium gets the hydrogen from here and the alkyl halide gives you the R here, and by then usual hydrolysis of these esters and this phthalimide gives you the required alpha amino acid. Now, I asked you why the combination, why there was a requirement of the combination happening. When phthalimide synthesis was also doing something, malonic ester synthesis is also doing something. So, there may be one point I made that there may be a problem with the yields. So, the better yields are coming in this combination. The other point is sometimes it is helpful in preparing difficult amino acids which require a certain number of groups to be introduced, and those groups are maybe there is some problem in introducing in phthalimide synthesis and malonic ester synthesis independently. So, I have taken the example of cysteine and proline. Cysteine is R group is CH2SH and proline is this only amino acid which is a secondary amine, or we sometimes called as amino acid. So, taking cysteine first, we take R group as PHCH2S CH2Cl. You have the R group here and reacted with the phthalimide in this form. We attack this R group here. When we attack it here, we get the CH2S CH2pH, and by using certain reactions which I am not going into, we remove this benzyl group and we get the cysteine molecule. So, this type of molecule required certain thing. So, it was given in the literature, maybe a high yielding process, an easy process, less side products. So, these may be the reasons for using the combination. Next is proline. It is pretty much interesting because we require the long chain to attack from the negative charge which is produced in the active methylene group of Phthalamido-diethyl-malonate to attack this CH2 removing Br, then CH2, CH2, CH2 Br is formed, and then the bromide is cyclized with the NH2 of the phthalamide which is formed NH2. The bromide goes away and we remove one HBr and cyclize the molecule. So, not going into much details, but I am telling you why we are using the combination of two synthesis. The reactant which is required is dibromopropane, 1,3-dibromopropane. The next synthesis is again we can say a little bit modification of malonic ester synthesis. We noticed that in case of malonic ester synthesis, when we were doing simple malonic ester synthesis, there was one introduction of NH3. The ammonia was attacking on an alpha halo acid. So, for that modification, what is done here is we take diethyl malonate, reacted with nitrous acid, we get the oxime, C double bond NOH. The oxime is formed in a reaction. We are losing 2 hydrogens of this carbon and 1 oxygen of this one to remove. We are actually, what we are doing, we are losing 1 water molecule, and then we reduce this oxime. We all know that by simple reduction with say nickel catalyst, we get the oxime reduced into the NH2 group. So, our problem of introduction of the amino group into the system is now solved. We are not using ammonia in this case, and then what we are doing, but you may notice here that we are not having the R group. So, we have to introduce the R group in this case. So, when we have to introduce R group here, we require diethyl malonate requires sodium ethoxide and alkyl halide, but those reactants may interfere with the NH2 free NH2 group. So, we are doing a simple protection here by acetyl chloride, and acetyl chloride gives you the acetylated amino group, that is CH3CONH, and then attached to the diethyl malonate. That is why it is called as aceta, this CH3C, amido, this is CH3CONH. So, this is group acetamido, this is malonic ester. So, malonic ester and acetamido making acetamido-malonic ester synthesis. Now, when we have protected the NH2 group, we can certainly react that with sodium ethoxide, creating a carbanion here, reacting with alkyl halide, putting a R here by the usual method, and then as we hydrolyze the carboxylic esters, the esters here, we also hydrolyze the amide here to get the required alpha amino acid. So, alpha amino acid is prepared here in this manner using acetamido-malonic ester synthesis. So, this is one modification of malonic ester synthesis which gives you a better yielding, and maybe certain number of amino acids are not prepared in other cases. So, the number of amino acids prepared may also change in this case. Moving on to the last synthesis of today's session, I would introduce to you the Erlenmyer Azalactone synthesis. This Erlenmyer Azalactone synthesis is the synthesis in which we are using the amino acid derivative. Already present amino acid derivative we are using. I have not taken here the general reaction. I am taking here in this case the preparation of phenylalanine as a special case, and this reaction you may note down that is useful mainly for the aromatic amino acids. So, phenylalanine, tyrosine and tryptophan are prepared by using this procedure. What is happening? Benzaldehyde is reacting with this molecule. If I just put something on this PHCO and make this NH2, instead of COPH I put an H here on this nitrogen, I would get NH2 CH2 COOH. By the whole of the things we are doing, by now you would understand that NH2 CH2 COOH is nothing else but another amino acid which is the basic simplest amino acid, which is called as glycine. So, what is this compound? This compound is benzoyl PHCO and glycine. Benzoyl glycine is nothing else but it is called as hippuric acid. So, we are reacting benzaldehyde with a substituted, or may say that protected in this case is not the right word because we would be requiring this group. So, substituted amino acid glycine. We are using an amino acid to prepare another one. So, we may take amino acid glycine, benzoylate it to get hippuric acid and then react with benzaldehyde. How does it react? What happens? The reaction is done in the form acetic anhydride and sodium acetate are added to it and we get this type of a molecule. Now, it requires some explanation, although I have not put it into slide because it would be taking away from the reaction, but it requires a certain amount of explanation how this cyclic molecule is being formed. Actually, what the reaction is happening here is this is acting as an active methylene group. We are using acetic anhydride which acts as a dehydrating agent. So, it is removing one water molecule as H2 of this, there is no hydrogen here now, this H2 is gone, this oxygen is gone and there is an double bond formation. As you would recall with no Venegal condensation or maybe a case of Claisen condensation, those type of reaction, something of that sort is being formed and it is much closer to the Novenegal reaction and we get alpha beta unsaturated carboxylic acid. But because of the presence of acetic anhydride, the further cyclization of this molecule here happens. How is it happening? You may put this C double bond O into the enolic form, right. So, you would be having double bond N and COH. So, OH here and carboxylic acid group was also here. So, carboxylic acid will lose OH and this OH will lose a proton to give you water again and this cyclization happens. This is nothing else but a formation of a lactone, C double bond O, O, COO in a cyclic molecule is called as lactone. A cyclic molecule, I am repeating, is having an internal ester. So, it is a lactone. But here in the cyclic molecule we have another heteroatom which is nitrogen. So, the word aza. So, azalactone synthesis, right. So, this azalactone which is formed is hydrolyzed to give you the similar kind of thing. Now, you can correlate with this reaction. If I straight away move to this, you would understand that nothing much has changed, but C double bond C is getting formed. The benzaldehyde and the hippuric acid is having a C double bond in between. Then what is happening? This alpha beta unsaturated carboxylic acid system is having, I am reducing this alpha beta unsaturated system with NaHg. What is NaHg? Sodium amalgam. So it is a reducing agent. You reduce it with the sodium amalgam. What I am reducing? I am reducing this double bond. This double bond is reduced. One hydrogen comes on this carbon, which was a quaternary carbon, it was having no hydrogen. Now there is one hydrogen coming here, and this double bond is, the pi bond is breaking and another hydrogen is adding to this carbon. So the CH is getting converted into CH2, CH2 CH, CH double bond C is getting converted into CH2 single bond CH. Now in the final step, I am having the hydrochloric acid, which what it will do, it would finally decompose this NHCOPH. Decompose is not the right word. It would hydrolyze this NHCO group, which is an amide bond, and amide is hydrolyzed to give you the benzoic acid. Benzoic acid is getting removed, and you would get the PH CH2 CH CO2 H NH2. So in our regular convention we should have written, I am usually writing this NH2 here so that you can understand this is the R group which is coming here, and R group is having the PH CH2 which is benzyl group, and we are getting phenylalanine molecule. So this is all about the synthesis of azalactone synthesis, Erlenmyer synthesis, but I have already told you that this Erlenmyer synthesis is usually used for only aromatic aldehydes. Aromatic aldehydes are used and aromatic amino acids are prepared. But what if I want to prepare the aliphatic amino acids using this? So there are certain modifications which are reported that in place of acetic anhydride, sodium acetate, lead acetate is used, or certain another kind of molecules are used, and we can use the aliphatic aldehydes to give you the aliphatic amino acids. So this is the synthesis of amino acids which we have done today, and in the further sessions we would be talking about using these amino acids to prepare the peptide molecules, and peptide molecules how they are synthesized using various amino acids, and we would also be learning about how to sequence the given peptide. A peptide is a long chain of amino acids joined together using the carboxylic acid of one amino acid, joining to the other amino acid using the NH2 group and forming a peptide bond, that is the amide bond. So how the amino acid A, amino acid B combines and then forms a peptide bond, then the peptide chain goes on, the peptide chain already available needs to be sequenced before it needs to be synthesized. That is what Frederick Sanger did with insulin. He got the two chains of peptides, of one was 20 something, the other was 30 something amino acids. He sequenced those two peptide chains, and when he got the sequence, how the amino acids are arranged, A, B, C, D, E, F, G, how this is arranged, the amino acid, the sequence was found out, and that later on he synthesized what is called as insulin today. So insulin he gave in this manner, and we would be discussing about the synthesis of peptides and sequencing of peptides in further sessions, and then we would be moving on to the structure of proteins and quaternary, tertiary and secondary structures of proteins in that manner, and then we would be winding up the amino acid, peptides and proteins topic. So thank you so much for your patience.
On that note, I would like to thank sir for this very interesting discussion, and I hope friends that you have found this lecture very informative, and I would like to thank you friends as well for watching our show. Stay tuned and keep watching. Thank you.